Hey there, physicists. This is Mr. Clegg, and we're going to talk about forces. So, a force. All right, force is the thing that causes acceleration. Actually, an unbalanced force is what causes acceleration. So, there's just a lot of stuff here on the screen that I already wrote so that it wouldn't take more time on the video. But I also want you to just write this stuff down. So, first of all, we're going to start with Newton's first law. If there is not a net force, then F net equals 0 on acting on an object, and then the acceleration is 0 of the object. This is basically what Newton's first law says. So a force is a push or a pull of anything. Different things can push. Magnets can push. You can have it with a rope or a string, friction, somebody's hand. Lots and lots of things can exert forces. But basically what Newton's first law is saying is that, if there's not a net force acting on an object, in other words, if there's no force acting on an object at all, which is very rare, in fact, on Earth, it's impossible because there's always gravity on Earth. Or if something has all the forces on it are balanced out by other forces. In other words, if you add up all the forces and they cancel out, then there's no net force on the object. Okay, and that means that the acceleration of the object is 0. Now, the way this was taught to me as when I was younger, I was a kid and I watched a lot of science shows and stuff like that. And in school we learned it this way. I didn't write it this way, but I'll say it. Okay, the way we learned Newton's first law is a body at rest will tend to stay at rest, and a body in motion will tend to stay in motion in a straight line at a constant speed, unless it's acted on by an unbalanced force. So that's just like a longer way, I guess, of saying, if there's no net force on an object, acceleration is 0, which means the object is either at rest or it's moving at a constant velocity. And we know that constant velocity means constant speed, straight line. Okay, so that's Newton's first law. This is also known as the law of inertia. Okay, Newton's second law says if there is a net force, then F net equals m times a. It's actually more commonly we use it this way when we're solving problems, but here is how we do it when we are, the original way I think of conceiving about what Newton's second law really is better in the way in the box here. So the way that works is like how much acceleration an object experiences depends on two things. It depends on the net force on it, and if that's stronger, then the object accelerates more. So if you double the push, then you double the acceleration. And that's seen here because this is in the numerator in the top, and this is also in the numerator. So double the force, double the acceleration. The other thing that affects the acceleration is how massive the object is. If the object has more mass, then the same net force will give less acceleration. And that's because the mass is down in the denominator. So if you double the mass of an object and keep the force the same, then you'll have half the acceleration, because you'll have, instead of m, you'll have 2m down here, and that 2m will be a half in front of this thing because the 2 is in the denominator. So double the mass, half the acceleration. Okay, now the great thing is, if you look at this equation and you figure out, oh, if the net force is 0, then you have a 0 up here. Then you also have 0 on this side. So really you don't need Newton's first law, because if you just plug in 0 for the net force, you get 0 for the acceleration here with the second law. So the first law is a special case of the second law. So I meant to say, because 0 is a constant, right? Anyway, let's move on. We're going to talk about some specific forces. Gravity is a force, and we call it Fg. The other word for gravity is weight. Those are the same exact thing. They're just different words for the same thing. And the force of gravity is the mass of the object times the acceleration due to gravity. So g is 9.8 meters per second squared downward. It's a vector. That's why we have a vector thing on top. Or it's also sometimes described as 10 meters per second squared when we're using an approximation. The force of gravity acting on a 1 kilogram object is 9.8 newtons, because you multiply the kilogram times 9.8 meters per second squared. And then you get this thing, 9.8 newtons. Now, what is a newton? I forgot to say that. force in general is measured in units of newtons. A newton is defined, triple equal sign means the definition. 1 newton is defined as the force it takes to accelerate 1 kilogram at 1 meters per second squared. So a kilogram is like 1 liter of water has a mass of a kilogram. So if you imagine a Nalgene bottle, it's a liter minus the plastic. So it's kind of, full of water, it's approximately a kilogram. Okay. So a Nalgene bottle is, a decent amount of mass, but no problem to lift it, obviously. So if you can imagine throwing that or somehow trying to accelerate, maybe moving it back and forth, if you can accelerate that kilogram by 1 meter per second squared, you're exerting a force of 1 newton on it. Now, most people are strong enough to probably accelerate that small mass by 5 or 10 meters per second squared, maybe even 20, 30. You could accelerate that mass fast enough that you could probably throw it across the room, in which case you're probably exerting, I'm guessing here, 30 newtons, 40, I don't know. So that's the way that works. But when that same kilogram is under Earth's gravitational pull, you're going to get 9.8 newtons. And this is always the case. It's a little bit confusing because a point of confusion, should I say, is that G is an acceleration when you drop something, right? Something accelerates at 9.8 meters per second squared. But in this case right here, we're not actually, my Nalgene water bottle could be resting on my hand here. I don't have a water bottle. Let's say I have a glass of water. So if this is resting on my hand, right? Imagine this is a full kilogram here. It's not, but so 9.8 newtons of force is what gravity's pulling on it, but I'm exerting a force upward to stop it. It's not actually accelerating right now, right? So its acceleration is 0, but this G over here is not the object's acceleration. It's just you multiply the mass times that G number to just get what the weight is. It has weight, even though it's not accelerating. And no matter what its acceleration is, the weight is always calculated using this G number. Okay. Just wanted to clear that up, and hopefully that will also get clear the more we do this. Okay, so weight is the force of gravity. It's measured in newtons. The SI system, the metric system, uses newtons to measure force, and weight is one type of force. There are many different forces. Now, mass is the amount of substance an object has, right? So if you want to know, like, how many molecules of water in this thing plus the glass, a way to measure that is with mass in kilograms, right? Now it's a little less, but I was thirsty, so there you go. So the amount of substance it has, you measured in kilograms. Now, if you had a very, very dense piece of gold or lead or something, you could have more kilograms in a smaller amount of space, a smaller volume, because it has a higher density. Or if you had a big, or for example, the air in this room is a lot less dense. So a kilogram of air is a lot bigger. But basically, it's the measure of the amount of stuff that's there. Okay. In the imperial system, which we use in the United States, the pounds, feet, inches, miles, that system, we use pounds for weight. So pounds are a unit of weight, newtons are a unit of weight, but remember that kilograms are a unit of mass. So on Earth, there are 9.8 newtons per kilogram, right? So 9.8 newtons per kilogram on Earth, and there are 2.2 pounds per kilogram on Earth. So there's a different conversion factor from pounds to kilograms, but that only works on Earth because remember that weight is the force of gravity, and that changes when you go to a different planet. But the mass does not. I'll get to the slugs thing in a minute. I know you're wondering what that is. So let's say you go to Mars, your weight would be less. If you go to Moon, your weight would be even less. And then if you go to Jupiter, your weight would be a lot more than it is on Earth. But all those planets, your mass would be exactly the same as it is here. In fact, even if you went to very far out interstellar space where your weight is 0, you'd still have the same mass in kilograms, but you'd have 0 newtons and 0 pounds. Okay, so the 9.8 and the 2.2 conversion factors depend on you being on Earth. Now, most of the time we're on Earth. We'll probably be on Earth for our whole lives. So that number is pretty good. But keep in mind that weight and mass are different things. Now, the unit of mass for the imperial system, pounds, feet, inches, that kind of stuff, the unit of mass is actually the slug. So we measure mass in slugs. Now, it's not really because I don't even know the number of how do you convert pounds to slugs. Slugs are a kind of obscure unit that only engineers in the United States and like 2 other countries use, because scientists pretty much always use the SI system, even in the United States. And in our daily lives, we usually talk about pounds. We're not really that concerned with slugs unless we are working in the field of engineering. And even then, sometimes engineers will use newtons and kilograms. So moving on, now we're going to talk about normal force. All right, so as I was mentioning just now, we have a glass of water on my hand, and it is not falling. It has weight acting on it, but it is not falling because I'm holding it up. So I'm pressing upward on it. I'm actually exerting a normal force on it. Now, if I set this over on the table, I know you can't see it, but if it's on the table, you can imagine there on the table, gravity's still pulling it down, normal force is pushing up. Those 2 forces are balancing each other out. So that's the same thing as my hovercraft here when it is turned on. And let's say there's no friction, you have the normal force going up from the floor, we have gravity going down. Those 2 are equal, so I put the little tick marks there to show that they're equal, even though I didn't exactly draw them equally. They're supposed to be equal. Our friction, we're assuming to be 0, even though that's not really the case. It's close enough to the case, and I want to show what it's like when you have a frictionless surface. So when we have something that is the glass at rest on the table, or even the hovercraft, when you first turn it on, it's at rest. It has no acceleration. That's how I know that there's no net force on it. But now let's say we give that hovercraft a push and it's sliding at a constant speed. Still has no net force because it's sliding at a constant speed in a straight line, I should have said. So it's going at a constant velocity. It's going at a constant velocity, then it has no acceleration. Now, if we were to do the same thing with the hovercraft turned off, let's say it's moving, it would very quickly come to rest. Actually, the hovercraft with the turned off would have so much friction, you probably couldn't even get it to move at all. But let's just say you gave it a push and it slid to a stop. Then what would happen is if it started out going to the right, the friction opposes it and goes to the left. And so you have normal force, gravity, just like before. The y direction balances out. So sigma means sum. So sum of all the forces in the y direction equals 0. And the forces in the x direction is only force of friction here, and that's in the negative x direction. I forgot to draw my axes, but we know it's negative. Let's just say that left is negative. And then that would be equal to the mass times the acceleration. In this case, the acceleration is also going to be in the negative x direction, and it's going to slow down and come to rest eventually. So that's how we do that. I just realized I forgot to define what normal means. Normal means perpendicular to a plane, so the normal vector is what's perpendicular. So if you have a table here, normal vector would be pointing upward. If it's a wall, then the normal vector points horizontally outward like that. So whichever direction the plane is, even at an angle like this, the normal vector, or a normal line, would be perpendicular to that plane. So that's what the word normal means in math and physics. Okay. Next thing, friction. There's 2 kinds of friction, static and kinetic. Static is the kind when things have a grip and they don't move. So your shoes on the floor under normal walking conditions that are not sliding, you have a grip. That's why you can walk. That's how you can walk up a hill even. Imagine if you didn't have friction, you would slip and then you wouldn't be able to walk up the hill. Imagine if you were walking up a very greasy hill or a very icy hill, it wouldn't work very well. So static friction is also what's needed for a car's tires to roll under normal driving conditions when there's nothing slipping. Kinetic friction is something that is when it's sliding. So this is kinetic friction. It creates heat sometimes. Actually, it always creates a little bit of heat. Sometimes it can create a lot of heat. And kinetic friction is what happens when you slip with your shoes, or car tires start to slip, or if an object is sliding down a hill, or even if you're dragging a box across the floor and it's kind of rubbing on the floor. That's kinetic friction. Rolling resistance is not really a type of friction, although sometimes people talk about it that way. It's what happens when your tires on a car or any kind of wheel, or even like a ball or something. Something's rolling and it just kind of gradually takes away a little bit of energy. So for example, if you push a car that's in neutral, eventually it will come to rest because of that rolling resistance, because the tires resist the motion just a little bit, but it's not sliding. And of course there is static friction there as well. But when you push a car, but the rolling resistance is just what causes the car to slow down a little bit over time. We don't talk too much about rolling resistance in this class, but just wanted you to know what that is, and that it's not really a type of friction, but sometimes people put it in that category because friction causes things to slow down eventually. And that's what happens there. Now, tension is the force of a rope or string or cable or chain. The direction of tension is along the direction of the rope. So you have a rope here. If you're pulling on something, you want to know what direction the force is. It's along the direction of the rope. We'll talk more about tension in a future class. The other force that you should know about is the applied force. So the applied force is a force from a push or pull from hands or other things like that. So if I push on something with my foot or a stick or my hands, or pull on something, usually applied force is something that comes from a human doing something, but it could be an animal, it could be a machine, whatever. It's not specifically, it's just kind of a force that's exerted by something that's conscious, not like gravity or something like that, and not like friction, which is a sort of a result of other movements, right? It's a little bit hard to define exactly what applied force is, but if you think about, a human doing some pushing or pulling, that's generally what applied force is. All right. Hope this was helpful, and I will see you in the next video. Take care.